Okay, so this is essentially the same scenario, but now this person here is moving away at the same time as uh, the rocket or whatever this is, projectile is moving up. Okay, so it's going to further change the angle at which the person is observing that projectile going up. So this is, it tells us that it's moving away from the projectile at 2 meters per second. So that's my dx by dt, and that's going to be how this person is moving along the x-axis. Now the x is at 100, but it's going to change. So we have a dx by dt. It's still, we're still measuring the change in angle in this same position. So we could still use the same triangle. So that's going to be 125 meters. And I can work out theta, but I could also work out any of the other trig ratios because I have the three sides. Okay, so how this changes the problem? Well, now that denominator is not just fixed at 100, it now has some value of x. And although we know what x is, we can now differentiate that x expression because it will change. So I'm going to start with tan theta is equal to now y over x. Okay, so when I differentiate this, I now have to differentiate this as a quotient. So I end up with secant squared theta times d theta by dt. That's what I'm solving for. And that's equal to, now this is a quotient, so I'm going to differentiate the numerator. So I'm going to get dy by dt times x minus y times the derivative of the denominator, which is dx by dt. Okay, which has been given as 2 meters per second. And then I'm going to divide that by the denominator squared. So whatever the x coordinate is, I can just square that. So basically I connected my variable, I figured out my variables, I connected them in an equation like I did before. I differentiate this with respect to theta, but now the right-hand side of this looks a little bit different because I had to differentiate x as a function. So I had to use quotient rule. So there's my expression. I can really plug in all my parts now because I have the value of secant theta. It was 5 over 4 when I simplified that. So I'm going to plug that in. So secant theta is 5 over 4. So I get secant squared. I'm solving for d theta by dt. So I'm just going to leave that as d theta by dt. I'm going to start plugging in some values here. dy by dt, I established as 25 meters per second. So this is going to be 25. The x position we have at 100. So I'm going to plug in the x value at 100 minus the y value was 75 in this problem. And the dx by dt is going to be positive 2 meters per second. Okay, and it's positive because it's increasing. I'm moving away from the projectile. Divided by the x position squared, well, that's going to be 100 squared. Okay, so then I just need to algebraically solve this for d theta by dt. That's going to give me that 16 over 25 on this side because I'm going to divide by, I have 25 over 16 on the left-hand side, so it needs to change to the left-hand side. I'm going to work this out as 2500 minus 150, and that's going to be divided by 10,000 when I square 100. Okay, so this is going to be 16 over 25. There's some common factors in here, but 2350 over 10,000. Okay, that factor of 25, I'm going to do 2350. Actually, I'm just going to work this all out. 16 divided by 25 times 2350 divided by 10,000. So I get 0.1504. Okay, so this is going to work out to be 0.1504, and this represents radians per second.